All right, so in our last video, we talked about how if we evaluate a function at a value, it's the same as finding the remainder. So here we use synthetic division and got a remainder of 16, which told us that f of negative 3 is equal to 16. But since f of negative 3 had a remainder, then x plus 3 is not a factor. So let's think about what it would take to have a factor. The factor theorem says that if we divide by the factor, so I'm going to actually put this in as a text box. So if x minus a is a factor of, let's stretch this out, it's a factor of our polynomial, then the remainder has to be 0. So in other words, p of a would be equal to 0. So here, a would be my root, so the remainder has to be 0. If we evaluate, we get 0. So let's think about, this is similar to what we've been doing in our previous notes, which is why I said, these notes might be a bit easier for you today. So show that this is a factor. Well, if it's a factor, then when we divide by negative 3, 1, 6, negative 1, negative 30, then the remainder should be 0, negative 3, 3, negative 9, negative 10, positive 30, remainder is 0. So since remainder is 0, then x plus 3 is a factor. And that means we have x plus 3 times x squared plus 3x minus 10. So our remaining factors, x plus 3, x plus 5, x minus 2 from factoring this. All right. So that's factor theorem, that the remainder has to be 0. Remainder theorem is just that, what we discussed up above. So remainder theorem says that if we divide a polynomial by x minus a, so if we divide a polynomial, we could call that p of x, by x minus a, then p of a is equal to the remainder.